It is a pleasure to welcome you to second edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. Today's lecture is on in-situ testing in geotechnical engineering, which will be delivered by Professor Emeritus Peter K. Robertson and Engineer Diego Marchetti. Dr. Peter Robertson brings more than 40 years of experience as an educator, researcher, consultant and practitioner specializing in the areas of in-situ testing and site investigation, earthquake design of geotechnical structures, and soil liquefaction. Peter is recognized as an expert both nationally and internationally in the areas of in-situ testing and soil liquefaction. He has been a consultant to various clients around the world for projects involving liquefaction evaluation for major structures, stability of onshore and offshore structures, landslides, stability of natural slopes and tailings dams, and used an interpretation of in-situ tests. He is the co-author of the primary reference book on cone penetration testing, CPT. He has also authored or co-authored over 250 publications as well as a popular CPT guide that is freely available on several websites. Peter has also assisted in the development of several inexpensive CPT-based interpretation software programs and has presented a series of free webinars in an effort to enhance education and practice. Peter continues to provide private consulting to a wide range of clients and currently resides in Southern California.
Thank you for that introduction. It's a pleasure to be here, obviously not in person, but virtually, but that has certain advantages because we can reach out to more people. And so the topic today is advances in CPT application, and Diego Marchetti is going to talk about advances in the flat dilatometer. And give you a little bit of background, that there is a book about the CPT. The book came out over 20 years ago. It's very comprehensive. It's got a lot of the theoretical background, etc. But because the book is actually quite expensive, I actually give out a free CPT guide, which is now on its 6th edition. It's shorter. It doesn't go through all the historical background, etc. So it's a very practical device that people can use in their office and in the field. And you can download a free copy from a wide range of sites. And also over the years, I've done a series of free webinars. They're also available on YouTube, but you can go to the Gregg Drilling website or just search onto YouTube and they'll pop up. There's about 17 of them, and they're each about an hour long. And so obviously in this talk, I cannot go into much detail, but if there are parts of what I talk about that you would like to know more about, then you're certainly welcome to go to some of those webinars and listen to them, and they will go into things in a lot more detail. So a little bit of history on the CPT. It was first developed in the 1930s. So, we're talking 90 years ago now as a mechanical device, but in the 60s, it really came as an electric cone. And so that's what, 60 years ago. So it's been around for 60 years. But in the 70s is when it really took off, and that was because there was a large amount of offshore investigations in the North Sea and in the Gulf of Mexico in particular. And because of the depth of water, it turned out that the CPT was really the preferred method to investigate the subsea conditions. So it really began to take off and gain a lot of interest in the 70s. And then since that, there have been lots of developments. Pore pressure measurements have become pretty well standard now. The equipment's become more reliable, the load cells and the electronics is much more reliable than it was back then. The addition of seismic measurements with geophones to measure shear wave velocity, and many additional sensors for environmental applications. But more importantly too, there's been a significant increase in the number of documented case histories. So over that period of time, more and more case histories have CPT data. And so we have much greater experience of CPT results with real world documented case histories. And of course, extensive amount of research, there's 50, 60 years worth of research at many different universities. So we have a great deal of knowledge about how we understand how the CPT works and how we interpret it and eventually apply it. So if you've not actually seen a cone before, it's a conical device that's pushed into the ground and it's got a conical point to it. In the early days, it was 10 square centimeters in cross-sectional area. Now increasingly, you see 15 square centimeter cones, which are just a little bit larger. Both are accepted by international and most national standards as the standard cone. And it has two load cells inside, one that measures the load on the tip, and when that's divided by the cross-sectional area, gives you the tip resistance in units of stress. And then there's a second load cell that measures the force of the soil as it passes by this sleeve friction. And when that's divided by the surface area of the sleeve friction, it gives you the sleeve friction or the sleeve resistance in units of stress. And then increasingly, there's a saturated porous element with a pore pressure sensor that measures the pore pressure during penetration. So the most common parameters are tip, sleeve, and pore pressure. Pore pressure usually measured on the shoulder just behind the tip. Sometimes it's measured on the face, but increasingly this location behind the tip is the standard, and that's often referred to as the U2 location, with U1 located on the face. Some actually try to measure both simultaneously, but it's generally easier to pick a location and stick with it, and the standard location is this U2 location. Another common parameter is this friction ratio, and that's the sleeve resistance divided by the tip resistance in percent. And so it's the relative friction. And those are the parameters you often see being used. And then the primary role of the CPT, it has four main applications. The first one is to determine stratigraphic profile and identify the materials. And because it collects data essentially continuously, you get a very detailed stratigraphic profile of the ground. And then because we measure pore pressures, you can also determine the groundwater conditions. Now, when you're pushing the cone in, you may be generating excess pore pressures due to the penetration process. These are sometimes referred to as dynamic pore pressures. And then if you stop the penetration and let those dissipate, eventually the pore pressures come to equilibrium, and you know what the equilibrium groundwater conditions are. And so you can get the groundwater conditions. And of course, over the years, there's now a wide range of parameters that you can get from the CPT, and I'll talk a little bit about that later, and also a wide range of direct geotechnical design. Foundation design is very common, both shallow and deep foundations, liquefaction assessment in seismic areas, and ground improvement, as well as other less commonly used techniques. Now, the advantages of the CPT is it's fast and continuous. So it's pushed in at 2 centimeters a second, which is approximately a meter a minute. And so you can do about a 30-meter sounding in about an hour. It takes a little over 30 minutes to get down, and then slightly less than that to come out. So you can actually do 30-meter soundings, or slightly less than 30 meters, approximately one every hour. So in a typical working day, it's not uncommon to do 5 or 6 of them in a day, depending on the spaces between the sounding locations. And it collects data on a depth increment. In the early days, it was to analog data collection. Now it's all digital, so it's digitized on a depth increment. Initially, it was common to digitize about every 5 centimeters. Now it's more common to digitize every 1 or 2 centimeters. So you get a lot of data when you push it in. And then the results are very repeatable and reliable. It's independent of the operator and the contractor. As long as people have equipment that fits the standard and the test procedures follow the standards, then the results are highly repeatable, and therefore the data is very reliable, independent of the contractor or the operator. And of course, that makes it very economical and productive. As long as you have equipment locally available, then it tends to be very economical and productive. There's a strong theoretical basis for interpretation. Over the years, a lot of numerical analysis has been done, as well as experimental work in the laboratory. And that, of course, is now supported by extensive case histories. So there's a strong theoretical basis. A lot of the interpretation is done semi-empirically, but all of them are supported by some sort of theoretical basis. It's just that the theory often has limitations to actually capture all of the real behavior of soils, and so semi-empirical correlations tend to dominate based on case histories. One of the big advantages is you have more than one measurements. So at a minimum, you have tip and friction, and increasingly common to have pore pressure. And then about 40 years ago, geophones were added to the cone. So you could also measure the shear wave velocity. And today it's becoming a little bit more common to try and measure the P wave velocity as well. And I'll talk briefly about that. The limitations of the test, somewhat high capital investment to buy the cones, the rods, the data acquisition system, and the pushing equipment. Although as years have gone by, that cost has steadily come down, and the equipment actually is remarkably inexpensive to buy. And the manufacturers now increasingly are making relatively small pieces of pushing equipment. So even the pushing equipment, the cost has come down considerably, and I'll show you some examples. You need somewhat skilled operators, but since most people nowadays are fairly comfortable with laptop computers, it's not so difficult to train people to follow the test procedures and monitor the data on a laptop computer. One common complaint, of course, is you don't get a soil sample while you're pushing the CPT, and often people use that as an excuse of why they don't like to use the CPT. That's actually unfair, because it is possible to take soil samples using the push-in equipment that you push the CPT in, and I'll show that in a moment. Obviously, penetration is restricted when you get into very dense ground, such as dense gravels or cemented layers and hard rock, of course. But basically, it's the same limitation that applies to the SPT, and you'll see later the flat plate dilatometer. There's similar sorts of ground conditions you can push it into. And here's an example of a push-in sampler, often referred to as direct push samplers. This particular one looks exactly like a CPT. It's about the same dimension. And so it's typically about 36 or even 40 millimeters in diameter. And it's got a conical tip. But there are no electronics or load cell inside. It's actually a sampler inside. And so what you do is you push the CPT first. You get a detailed stratigraphic profile, and then based on that profile, you move over a short distance, typically about 1 meter, and then you push in these samplers, and then you go to the required depth where you would like to take a sample, and then when you get to the depth, you pull back to expose the sampler and then push the sampler in to obtain the sample and then retrieve the sampler. There are many different types of push-in samplers. This is just one example. They vary in diameter and length depending on how soft the ground conditions are. The key thing to keep in mind is that you've got a detailed stratigraphic profile, and so you identify the layers you're most interested in based on the project requirements, and then you can obtain small disturbed samples. They are disturbed because they're thick-walled, small diameter samples, but they're ideal for index testing such as grain size and Atterberg limits, just to verify the classification of the soil, but not for strength testing. Another thing to keep in mind is, although the CPT is pushed in at 2 centimeters per second, when you're taking samples, you can actually push in faster depending on the type of equipment. And the type of equipment that we use quite commonly here in North America are these big trucks, and they can often push in 10 or even 20 times faster. So you can get down to 10 or 20 meters in literally just a couple of minutes to take your sample. So it's not time consuming to get these samples. Here's an example of different types of pushing equipment. Up in the top row there, you see these trucks. Top left-hand corner is actually one of the trucks here in California. They're typically 25 tons or 250 kilonewtons, and you push from the center of gravity. And so you can push the full 25 tons on this relatively small diameter probe. So you can apply a very large tip stress. So you can apply tip stresses close to 1,000 atmospheres of stress. So you can push through very hard material, as I'll illustrate in a minute. And there are track-mounted versions. And with these trucks, typically what you do is the trucks have a series of jacks in the corner. And so when you get to the location you require, you can lift the vehicle up off its wheels to create a level, stable platform for pushing. And a lot of the trucks here in North America, they have little video cameras underneath that are connected to the driver. And so the driver can see where the truck is relative to the location you would like to push the CPTs. So it's very quick to align it over some sort of hole. And in recent years, there's a growing number of these small pieces of equipment that are often track mounted, but because they're very lightweight themselves, they usually have self-anchoring systems. On this particular one, you can see that there are two augers with their own little motors. And so you self-anchor the device down to create the reaction that you need to push the cone in. And in the bottom left-hand corner, you can see there's a small track-mounted auger rig that's had an auger installed, and the rig is chained to the auger to create the reaction to push the CPT. And then this little rig on the right is another simplified piece of equipment attached to a front-end loader. So there's a variety of equipment out there for pushing. In recent years, there's been a growing popularity in sonic drilling, because sonic drilling is very rapid and gives you a continuous core. And so here in North America and in other parts of the world, sonic drilling is becoming very popular. And there's a number of companies that manufacture sonic rigs, and one of them also makes a CPT unit that can be attached to the clamps of the sonic rig, so that you can do a standard CPT testing with a sonic rig, and then after you've done the CPT, you can pull the CPT out and then drill and take samples, either at the same location or move over. And also, because of that, they've also developed a sort of a simplified cone that can actually be pushed in directly with the sonic rig. And then if you encounter a hard layer, such as a gravel layer, then you can turn the vibration on the sonic rig and vibrate the cone through the hard layer. And then once you're through the hard layer, resume pushing statically without the vibration to get the CPT data. And in the offshore industry, as offshore got into deeper and deeper water, they developed wireline CPT systems for deep offshore. And now that equipment is being miniaturized, and some contractors are now beginning to offer wireline CPT with sort of more conventional borehole sizes for onshore work. And so here's an example. You can see the cone protruding out below the drill bit. Everything's laid horizontally so you can see it. And so what you can do is you have a drill rig, and you can drill to a required depth, take samples, and then you can wireline down the CPT very quickly, push the CPT typically for 1 to 3 meters, and then collect the CPT data, pull the cone back out with the wireline, and then continue drilling and sampling. And in the offshore industry, it's common to alternate between the two, where you push the cone and then drill, take samples, push the cone, and then repeat with the samples. So this gives the possibility to do CPTs at depths greater than 100 meters. It's quite rare to see CPT pushed from the surface to depths greater than 100 meters, and that's partly because of the buildup of friction along the push rods. But the wireline allows the ability to push CPTs much deeper, and also push CPTs more efficiently when you've got very difficult ground conditions, possibly like a rock fill embankment that you would like to drill through, and then push CPTs in the softer soils below. And so wireline allows you to do those sorts of things. Let me go back here. Often I'm asked, how deep can you push the CPT? And that really depends on how much reaction force you have for pushing the cone, and the amount of rod friction that develops, as well as how hard the ground is. And I mentioned earlier that 15 square centimeter cones, which are 44 millimeters in diameter, are becoming more common. And the original 10 square centimeter cones are pushed in with push rods that are also 10 square centimeter. And so you can develop a lot of rod friction. So in the early days, the Dutch who developed the test identified that you needed to put a bump in the rods a short distance behind the cone so that you could push the soil away from the rods so you could minimize rod friction. But the advantage of the 15 square centimeter cone is it's already larger than the push rods, so it already minimizes the rod friction. And so this little graph illustrates the push force required as a function of SBT N60. And so you can see that if you've got 20 tons or 200 kilonewtons reaction force, you can actually push into ground with blow counts higher than 100 blow counts. Now, keep in mind that the SBT blow count starts to become unreliable past 50 blow counts per foot. And so the relationship between resistance and blow count no longer continues to be linear. Whereas with the CPT, you can continue to push into very hard materials. And I live in Southern California, and in Southern California, we have quite a lot of soft rocks, sandstones, siltstones, and claystones. And it's quite common to push CPTs fairly significant distances into these soft rocks in this region. When it comes to CPT interpretation, and I've added CPTU, that's the common acronym to define that the CPT has pore pressure measurements. So this is a little diagram, tip, friction, and pore pressure, and sometimes shear wave velocity. And of course, primary thing, often you get the soil profile. You can estimate the state of the soil, relative density or state parameter, or OCR if it's clay. You can estimate the strength of the soil, either the friction angle in sandy soils or the peak undrained strength in clay soils. And you can also estimate the remolded undrained strength in clays, and you can estimate the stiffness. And of course, if you measure the shear wave velocity, you actually measure the stiffness of the ground. Although it's a small strain, you do measure the actual stiffness. And as I said, you can get the stress history, the OCR, and from that, the pre-consolidation pressure. And you can also estimate the one-dimensional compression index, compression modulus, or the compression index. And if you stop in clay layers where there's excess pore pressure and let those pore pressures dissipate, the rate of dissipation, which is often captured by the time to dissipate 50% of the excess pore pressure, T50, and then you can estimate the permeability and the coefficient of consolidation. So from these measurements, you can actually estimate pretty well most of the parameters you would be interested in for design. Now, over the years, lots of sensors have been added. I've mentioned pore pressure. That's now very common. All cones have a simple inclinometer in to check that they're maintaining essential vertical as they're being pushed in. And I mentioned that geophones are commonly added, and I suspect engineer Diego Marchetti will talk about seismic DMT. So now it's quite common to have geophones and measure the shear wave velocity and or the P wave velocity to give you a measure of the stiffness of the ground. And in recent years, people have put cameras in so you can actually look at the soil. This has tended to find more application in environmental applications where people want to see the detailed layering as well as possibly the type of contaminant that's in the ground. And then for geoenvironmental, there's lots of additional sensors. We won't have time to talk about it here, but in North America and in Europe, geoenvironmental issues are a growing concern. And so CPT is often used to put these added sensors in to gain more insight into chemical contaminants within the ground and groundwater. Now, I've borrowed this slide from Professor Paul Main, and it illustrates how powerful the seismic CPT with pore pressure measurements is, because you get 7 measurements. You've got tip, the sleeve resistance, pore pressure, shear wave velocity, and P wave velocity, the rate of dissipation, which is often captured by T50. And then if you let it go all the way to equilibrium, you get the equilibrium pore pressure and you get the inclination. So you get up to 7 measurements with one simple test that provides you a lot of information about the ground conditions. When you think that most constitutive models that try to model the real behavior of soil often require 10 or more parameters to capture the behavior of the soil, then clearly you need a test that has more than one measurement to try and give you insight to the real behavior of the soil. And with the seismic CPT, with pore pressure, you've got 6 or 7 measurements that provide you a lot of insight into the real behavior of the soil. This slide is also borrowed from Professor Main, and it's quite a nice slide where he sort of compares the conventional drilling and sample with the sort of modern direct push technology with the CPT here illustrating the seismic CPT. And you can see in the old days, common to drill boreholes, maybe do cross hole to get seismic measurements, the SBT to get N60, maybe vein shear test to get undrained strength and sensitivity, maybe pressure meter testing to get modulus, and so on, and Packer test to get permeability. Whereas with the seismic CPT, you can essentially get all of that information in one test that's clearly very cost effective. Now, since soil profiling is the most popular application of the CPT, I'll just talk a little bit about recent developments in soil profiling. Obviously, its advantages are it's fast, cost effective, and you get a continuous profile. You get detailed stratigraphic profile based on multiple measurements. But the soil classification from the CPT is not exactly the same as traditional classification based on samples and index testing. Now, just to remind everyone, traditional soil classification here in North America, the unified soil classification system is the one commonly used, but all systems around the world generally follow the same basic approach, and they're all based on physical characteristics on disturbed samples of the soil. So if it's a coarse grain material, you run the material through a set of sieves to get the grain size distribution. And if it's a fine grain soil, you perform AGERP limit test to determine how plastic the soil is. And so clearly they're physical characteristics, and they're carried out on disturbed samples of soil. So they only have a very loose connection to the true in situ behavior of the soil. Whereas a CPT classification system is a behavior-based system. And since the CPT responds to the in situ strength, stiffness, and compressibility of the soil, you're getting a behavioral classification, which is not exactly the same as the physical classification system, or sometimes referred to as a classification system based on textural detail. AGERP limits and grain size distribution. And this is a common mistake people make, where they take the CPT classification, they compare it with samples, and then occasionally they're surprised when the two don't exactly agree. And that's because the CPT is telling you how it's behaving like, not what it actually is based on physical characteristics. So that's why it's nice to get small disturbed samples so that you can also do a classification based on the physical characteristics and compare the two so that you have a broader understanding of both its in situ behavior and its physical characteristics. So way back in the mid 1980s, I developed a set of curves with Professor Campanella, and the early curves, they evolved out of the work out of Holland, where they noticed that tip resistance and friction ratio seem to respond to the type of soil. So this early chart has tip resistance on the vertical axis and friction ratio on the horizontal axis. And sandy soils tend to have high tip resistance and low friction ratio, and clay soils tend to have low tip resistance and high friction ratio. And sensitive soils have low tip resistances, but also can have very low sleeve friction, because the soil, as it passes the sleeve friction, essentially becomes remolded. And so you get very low sleeve frictions and hence low friction ratios. And then cemented and soft rocks tend to fit in the upper right-hand corner. And then in the mid-90s, these charts were color-coded because color printers became more popular. And so the charts had colors put onto them, which was rather nice, because then you could not only go by the zone that it was falling in, but also you could assign it a color so it was more visually appealing. And so this is the sort of result that you got, where you would get plots of, here it's showing tip resistance, the friction resistance, and then the friction ratio, the pore pressure, and then on the right-hand side is the computer is generating the soil behavior type, and you can see that it's color-coded, and the length of the bars actually represents the zone of the chart, and then the computer writes in words what they are. So you can see a lot of information, and this particular example you can see illustrated, there's about 6 soil samples were also taken, and the location of them are identified. This particular example, you can see that the upper 30 feet is softer, fine-grained materials, mostly silts and clays, and then from 30 feet down to 100 feet, or roughly 30 meters, it's mostly sand. And there's 2 types of sand. There's an upper sand that's a little bit looser than the deeper sand, and the upper sand is mostly clean, very low friction ratio with very little changes, and the pore pressures during pushing are hydrostatic. So it's a clean, free-draining sand, whereas the denser sand below is a little siltier. It's got some small silt lenses in it, and it must be siltier because it's actually generating a little bit of excess pore pressure. And because it's a dense sand, those excess pore pressures are negative of hydrostatic. They're still positive, but they're negative of hydrostatic. So this lower sand is a dense, dilative, silty sand. So you can see a lot of information can be gathered quickly. And as I said, this is about 100 feet deep or 30 meters. And so this data could all be collected in about 1 hour. Now, in the mid-80s, Professor Roth, who was at the University of Oxford at the time, quite rightly suggested that CPT interpretation should be done with normalized data. So just as with the SPT, where there was a recognition that ideally you should normalize the SPT both for energy to get N60, but also for overburden where you would get N160. So the CPT was the same, and Roth had suggested it should be the net cone resistance divided by the vertical effective stress, and then there would be a normalized friction, which is the sleeve friction divided by vertical effective stress, or also the friction ratio. And then if you've got pore pressure, you can have the excess pore pressure divided by the net cone resistance, or increasingly the excess pore pressure also divided by the vertical effective stress. But what we realized is Roth's recommendation was based mostly on clays, where that normalization works very well. But when you get into sands, that simple linear normalization doesn't work so well. That sands of a constant relative density the tip resistance doesn't increase linearly, it increases non-linearly. And so we recommended that the normalization should be modified slightly. And here it's the net cone resistance divided by atmospheric pressure. So the net cone resistance is dimensionless. So it doesn't matter which units you're using. And then instead of dividing by the vertical effective stress, it's atmospheric pressure divided by the vertical stress to the power of n. Now, if n is 1 in clay, you come back to Roth's simple normalization. But in sands, n is often closer to 0.5. And so there's a small iterative process to get the correct n value, to get the correct normalized value. And then in 1990, I sort of updated the chart and said, yes, we do need to go for normalized. So the chart was updated to show normalized cone resistance against normalized friction ratio. The friction ratio was also put on a log scale. And when that was done, the boundaries essentially became concentric circles, which was rather nice. And we could identify a zone down the middle that said, this is where most normally consolidated young soils would fit. And if you had older or heavily over-consolidated soils, they tended to move up to the top right-hand corner, and very loose, sensitive soils tended to plot in the lower left-hand corner. And it was Mike Jeffries and Mike Davies in the early 90s had suggested that since these boundaries were approximately concentric circles, you could define a single parameter, which they called the soil behavior type index, IC, and it was essentially the radius of these concentric circles. So when IC was about 1, so there was an imaginary center of a circle up here. And so when IC is about 1, you're in the top left-hand corner of the chart. And when IC is about 4, you're down in the bottom right-hand corner. So it was a simple way of combining the two measurements into a single parameter that could be used to approximately identify what type of soil you were. And from that, we identified that this boundary of an IC of about 2.6 was the approximate boundary that separated coarse-grained soils that were generally free draining during the CPT to fine-grained soils that generally were undrained during the CPT penetration. And also, this IC became very useful for iterating to get the stress exponent for the normalization. So you start off with a stress exponent of 1, calculate the normalized cone resistance, see where you fit on the chart, and then based on the IC, you update it with this little equation to go to the next iteration of the stress exponent. And then usually after about 2 or 3 iterations, you get the correct stress exponent. And most software programs now build this in automatically. And we'll talk about that later. And so recently in 2016, I updated the chart again, and that was partly because of the confusion that many people were having between the soil behavior type classifications on these charts compared to the traditional classification based on physical characteristics. So I wanted to go to descriptions that were more behavioral. So you, instead of calling it sand, silt, and clay, we changed it to sand-like and clay-like. And because it's normalized and it's based on predominantly young, uncemented soils, then we could also show a line that separates soils that were either dilative at large strain or contractive at large strains. So dense soils that tend to dilate during shear plot in the upper right-hand portion of the curve, and then looser soils that are contractive in shear plot below that line. So now you've got sand-like dilative soils, sand-like contractive soils, clay-like dilative soils, and clay-like contractive, and then you've got clay-like contractive and sensitive soils. And I simplified and expanded the range of the sensitive soil to capture more of the soils that were sensitive. And then recognize that there was a transition zone in the middle where soils would transition from sand-like to clay-like, just like the Atterberg limit classification charts recognize that you transition from silts into clays as you go from sort of low plastic materials into high plastic materials. And so this chart now is becoming more popular. And I also modified the boundary. Instead of concentric circles, I went for a more hyperbolic shape, which actually captures the real behavior once you get up into these regions of soft rocks and way into the region of low friction ratios. Now, also in that paper in 2016, which is in the Canadian Geotechnical Journal, we also recognize that most of the data used to develop these charts are essentially relatively young, Holocene age soils that have little or no cementation. So they're young, they're unaged, and they have little or no cementation. So they have little or no microstructure. But when you get into soils that have significant microstructure, such as heavily cemented materials or very old deposits, then their behavior is slightly different. Often they're stiffer than you might expect because of their age or cementation. And so these charts may be a little bit misleading. And so we recognize that there was a need to identify whether or not soils had some form of structure. And here I'm separating that macrostructure is the layering and fissuring that you can see, and microstructure is the structure that you cannot see. It's occurring at the particle scale, and it's dominated by things such as aging and bonding. So we know that very old soils tend to be stiffer at small strains, and we know that cemented soils are also much stiffer at small strains, but also stronger until you break the bonding, and then they can become back to behaving like an unstructured soil. And so we also recognize that the CPT penetration resistance, the tip resistance, is mostly controlled by the large strain response because you're shearing the soil as you push it in. So it's controlled primarily by the peak strength of the soil. Whereas when we measure the shear wave velocity, that's a small strain response. You're measuring it at a very small strain, usually 10 to the minus 4%. And so it's controlled by the small strain stiffness. So when you do seismic measurements with the CPT, you've got a measurement of the strength and a measurement of the small strain stiffness. And for young uncemented soils, those two link reasonably well. Whereas for older or for cemented soils, they don't link. And so you have what is often referred to as unusual soil behavior. And that disconnect between the two allows you to identify whether or not there's significant microstructure. So we had suggested this relationship, which is the normalized cone resistance plotted against what's referred to as the rigidity index, which is the small strain shear modulus divided by the net cone resistance. And it's useful to remember that the small strain shear modulus is just the shear wave velocity squared times the mass density. And the mass density is just the unit weight divided by gravity. So when you've got shear wave velocity, you've got G0. And then, of course, the cone resistance, the net cone resistance, which is a measure of the strength. So it's a stiffness to strength ratio, which is often referred to as rigidity index. So I've called it the small strain rigidity index. And the sort of these lines, what we find is that most young uncemented soils fit within a fairly narrow band with this, what I refer to as this normalized rigidity index, which is this stiffness to strength ratio multiplied by the normalized cone resistance to the power of 0.75. Initially, we thought it was to the power of 1, but actually 0.75 fits the data better. And so most young uncemented soils fit within that narrow range, and I'll illustrate this in the next. So in the paper, I looked at about 35 case histories from around the world, half of which were in young, uncemented sort of ideal soils. And then the other half were in soils that had significant microstructure. Either they were cemented or they were aged, or some of them had unusual mineralogy, and they all tended to fall outside that region. So this normalized rigidity index of about 330 is roughly the dividing line. And so very young deposits tend to plot, recently deposited, say tailings, for example, often fit closer to a kg of around 100. And then so Holocene, the average Holocene value is often around 200. And then as it gets towards Pleistocene, it starts to approach 300. And once you get older than Pleistocene, you get outside that region where you get significant effects of aging that could influence the interpretation. So combining all that together, there's actually a set of 3 curves, one which is the chart based on tip and friction ratio. The middle one is tip and the pore pressure, the normalized pore pressure, which is the excess pore pressure divided by vertical effective stress. And Professor Schneid with Randolph and Main had published a paper suggesting this chart. I just made some small changes to it to match the other chart. And then this new one based on shear wave velocity. So now you've got 3 charts, all based on normalized parameters. So the one on the right is shear wave velocity and tip resistance. The one in the middle, which is mostly for fine-grained soils, is excess pore pressure and tip resistance. And then the one on the left is friction ratio and tip resistance. So ideally, you look for commonality, that they're all giving the same. So ideally, use the shear wave velocity first, determine whether or not it's ideal soil, relatively young and uncemented. So there's little or no microstructure. So now you have more confidence that the other 2 will work, particularly the main one, which is tip and friction ratio, which has that boundary between contractive and dilative. So then you have confidence that works. If the soil has significant microstructure, then this dilative contractive boundary may not be correct and may migrate a little bit with increasing microstructure. And on the middle chart, Schneid et al. Yeah, that's correct. They had shown that in sort of ideal young soils, if it's a normally consolidated clay, you get a low tip resistance and some excess pore pressure. And then as the clay becomes slightly over consolidated, the tip resistance climbs and the pore pressure increases as well. And then once you get into a condition where the soil is now over consolidated with an over consolidation ratio sort of greater than about 4, it starts to become dilative at large strains. So the pore pressures start moving towards negative. So it starts to move into the negative region. But if you've got fine-grained soils that has significant microstructure, it is possible that you can have these very high tip resistances, but when you break the bonding, you get these very large excess pore pressures. So in things like siltstones, for example, or cemented silts, you can get high tip resistance, which is reflecting the strength of the cementation, but you also get very large excess pore pressures, showing that once the cementation is broken, the material is in fact contractive at large strains. I mentioned about dissipation tests, and this is a quick example. This is a plot in tailings of tip resistance, friction ratio, and then pore pressure, and a number of dissipation tests were done. And if you do a number of dissipation tests, you can determine what the piezometric profile is. And on this particular one, the groundwater was at about 3 meters. The blue line represents the hydrostatic line, but the red line represents actually what the equilibrium dissipations gave, which shows that it's less than hydrostatic. So it's indicating there's downward flow as the water is flowing laterally and downwards. And then on the right, here is an example of one of those dissipation tests. It's pore pressure against log time, and it's illustrating that the time for 50% dissipation in this case is 85 seconds. And because the dissipation is logarithmic, it actually takes roughly 10 times that to get to 100% equilibrium. And so because of that, so when it's plotted against log time, you get this S-shaped curve. So it's a little bit harder to know exactly where equilibrium may be, especially if you stop early. Whereas if you plot it against square root time, theoretically it comes down as a straight line and then curves over to equilibrium. And so it's possible to, it's easier to project to equilibrium for shorter dissipations if you plot it in terms of square root time. And so often for short dissipations, it's a little easier to plot it in terms of square root time. When it comes to application, in geotechnical design many years ago, I suggested that there's two broad approaches. One is the direct approach, which is empirical in nature. It's based on past performance, and you basically go directly from CPT to foundation design based on past performance. But also there's the indirect approach, which is where you first of all estimate geotechnical parameters and then put that into a model and then predict performance of the structure based on those geotechnical parameters. So you've got both approaches. One requires geotechnical parameters, the other one basically requires empirical methods based on past performance. Now, if we had more time, I would illustrate some examples because when you go through the webinars or you read the CPT guide, you see that there's lots of methods available to interpret parameters. And often people think, wow, this is quite complicated to do this interpretation. And I'm going to have to write a big spreadsheet to do this, which can be problematic, verifying that the spreadsheet's actually working well. So about 10 years ago, I got involved with John Ioannidis in Greece, and he has a small company called Geologist Mickey, and together we developed this CPT interpretation program. I don't have any ownership in the software, and I don't get any return for the software, but I helped develop it because I wanted to have easy to use software easily available. And the software is sometimes people will pronounce it CPT-IT, but John put that lower script E in there, so it's actually pronounced C-petite. So it's a sort of play on words that petite is French for small, and so it's a small CPT interpretation program. So it's pronounced C-petite. Now I don't have time to actually go through it, so I've just taken some screenshots just to illustrate how easy it is to get all the information off the CPT. So here's a screenshot. It actually shows 11 different CPTs from all over the world. I've just selected this published one from the Venice Lagoon, which is in Venice, Italy. And they did a tank loading test to see how much settlement would occur in these soft alluvial deposits. So here you've got tip resistance, friction ratio, pore pressure, and the soil behavior type. Notice here, quite a clever innovation, that the soil behavior type charts were color-coded. And so the innovation was that you can choose to put the color of the soil behavior type underneath the cone resistance. So you see both the cone resistance and the soil behavior type collectively together. And in this particular example, you can see very clearly the sands are sort of brown and the silts are green and blue, silts and clays. So the brown layers are clearly the sand layers, and the softer silts and clays are the softer layers. And the water table is close to the ground surface. It is roughly hydrostatic, and you can see that pushing through the sand, it's basically hydrostatic. And then when you encounter the soft silts and clays, you get large excess pore pressures that, if you stop and do dissipations, come back to the equilibrium. And then this is a plot of normalized parameter. This is sort of the updated normalized. So the normalized cone resistance, normalized friction ratio, the normalized pore pressure, and on the right is the updated normalized soil behavior type with this updated soil behavior type index IB. And here you can see it says clay-like and contractive, sand-like and contractive, etc. And then you can see how the data plots, and they had shear wave velocity. So over on the right-hand side, you can see the shear wave velocity data was imported into the software, and you can see that the data falls within the band, and most of it is actually close to the lower end, illustrating that this is a young Holocene deposit with little or no aging and little or no cementation. And the excess pore pressures are doing what you'd expect, high pore pressure, relatively high pore pressures in the clays. And then when they're over consolidated, or when you get into the sands, you get essentially zero excess pore pressures. And on the right here, you can see that most of the soil is contractive, and then some of the sand layers are sand-like and dilative. And the software allows you to interrogate the data on a point-by-point basis and also look at the values. There's a wide range of parameters that you can estimate, and so you can estimate the permeability based on the soil behavior type. Note that this goes 10 orders of magnitude across here on a log scale. You can also estimate the equivalent SBT N60 value, the Young's modulus in sands, the relative density in the sand layers, and the friction angle in the sand layers. And you can also estimate the one-dimensional constrained modulus, the small strain shear modulus, assuming it's young and uncemented. And then you can estimate the peak undrained strength, which is in black, and the remolded undrained strength in red. And then here's the undrained strength ratio and the OCR. And you have the option to click on the OCR plot and flip it over to pre-consolidation yield pressure, if you would prefer to look at it in that terms. And then for design, for footings, people often like to estimate what the ultimate bearing capacity of a shallow footing is. And rather than apply bearing capacity theory and parameters, it's been observed that there's a direct link between the average cone resistance underneath the footing and the ultimate bearing capacity with this correction factor. And the correction factor is around 0.16 for sands and up around 0.3 for clays. And so the software allows you to select the average RK value, and it defaults to a value of 2. So if you have mixed sands and clays, it goes halfway between the two. And the zone of influence is 1.5 times the width of the footing. And so here's an example where it's calculated from a very small footing, only 1 foot wide, up to a very huge tank, which is what was placed on this site. So a 50-foot diameter place. I apologize. This one is imperial units. The software actually defaults to metric. It's just that I happen to show one in imperial units since I'm in the US. And then with that, so once you've got an estimate of the ultimate, if I go back, so the ultimate bearing capacity varies from as low as 4, this is tons per square foot, or it could be 4 atmospheres of pressure, with a sort of an average around 6. So in this particular case, if you had a 50-foot diameter tank and it roughly had about 1 atmosphere of applied footing pressure, so 1.1 TSF or 1.1 bars, and it was embedded a third of a foot down, and it was a circular flexible tank. And so here you've got the tip resistance, the one-dimensional constrained modulus, and then you've got the yield stress. And then the green line shows you the in situ effective stress, and the red line is with the final stress with the tank in place. And then the right-hand side shows the cumulative settlement. And then if that's not good enough, you can actually estimate pile design. So it uses the LCPC method, which is based on a large number of full-scale instrumented pile load tests in a wide range of soil types and wide range of pile types. So you get to select the pile type, you put in the size of the pile, and you've got the default factors of safety, but you can modify those. And the red line is the cumulative shaft resistance, and then the blue line is when you add on the base resistance. And these are all allowable capacities with those factors of safety. A higher factor of safety put on the base, and a slightly lower factor of safety on the shaft resistance. And then you can estimate the load settlement of a single pile. And this is based on a simple bilinear load displacement relationship for both the shaft resistance and the base resistance. And you just add the two together, and all you need to input is the displacement required to mobilize that. So often very small displacement to mobilize the shaft resistance, and often a larger amount of displacement to mobilize the base resistance. And when you add the two together, you get an approximate load settlement curve, and then it also shows you where the allowable load was. So to summarize then, CPT interpretation should always be done within a geologic framework. You have to understand what the geology is, and then CPT can provide good estimates of a wide range of geotechnical parameters in most, well, it says fine-grained soils here, but most soils. It's best to view the parameters as a profile, like I illustrated. So the program, for example, that when you estimate parameters, the program allows you to import other measures. So for example, if you did field vein testing and you had both peak and remolded undrained strength from the field vein test, you can add that into the software, and it plots those data points over the top of the CPT. So you can see whether or not there's good agreement and whether or not you want to modify the interpretation of the CPT to match the field vein. And of course, if you've got lab data, so you've got OCR and pre-consolidation pressure, etc. And if you've got 1D consolidation test and you've got the constrained modulus, you can compare it with the estimated values. So you can import all of those. And it's best to do it on a profile, because then you're also seeing the stratigraphy. And CPT can provide a wide range of direct and indirect design methods, of which I touched on very briefly, and hopefully illustrated that software makes this a lot easier for you now. The software has been around for 10 years. This particular one's, of course, has many users around the world. And so all the bugs have been sorted out, so you can ensure that it's doing the calculations correctly. And so you feel a little bit more confident in using it. So in summary, the CPT is fast, it's very reliable and cost-effective means to evaluate detailed soil profile, estimated geotechnical parameters, groundwater conditions, and actually perform preliminary geotechnical design. And increasingly, I encourage people that when you're supervising CPT in the field, it's useful to take a laptop computer with you and have software like the one I showed, and start to actually look at the data in the field and start to do preliminary interpretation in the field, so you can decide where you might want to do dissipation test, where you might want to take samples that are relevant for the particular project. And it's easy enough to do that in the field while you're collecting the data. And because the data is digital, sometimes that information can be emailed directly to, say, a project engineer in the office, and they can do it in real time in the office. Both options are available. It's suitable for a wide range of soils, except, of course, very dense gravels and hard rock. And then advances made in CPT equipment and design applications in recent years are supported by a long history of research and large number of documented case histories. And so in summary, the CPT, particularly with pore pressure measurements and with seismic, is now becoming the most common in situ test in most soils around the world. And so you really see it gaining acceptance now. It has been around for over 70 years, and so now it's becoming the most common test. So that concludes my presentation. I know I moved along relatively quickly, but it is recorded, and so you do have the opportunity to go back and look at it at your own speed, as well as possibly going to some of the webinars that are recorded. They're available on YouTube, and you can go into those as well that go into some of the elements I talked about in more detail. So I'm happy to take any questions. Okay. The key test for pore pressures is stop and do a dissipation test. So if you're getting negative pore pressures and you're concerned that are they real, then stop and do a dissipation test. So if the porous element has become unsaturated, possibly due to either poor saturation procedure to start with, or that you were pushing through a relatively deep profile of unsaturated material, and therefore you lost the saturation of the porous element. Then when you're below the water level, if you stop and do a dissipation test, then if there are any small air bubbles in solution, air bubbles in the filter, then they will quickly go into solution and resaturate the cone. So if you're below the water table, you do a dissipation test. When it comes up to equilibrium, which is a positive pore pressure, it resaturates the cone. And then when you start pushing again, if it immediately goes negative, then it's telling you that's the response of the ground, not because it's unsaturated, because if it immediately goes negative, it's telling you the soil is dilative in shear at large strains, and those negative pore pressures are real. Now, obviously negative of hydrostatic, but they can also go negative of 0. But once they get below about 1 atmosphere, in other words, once you go minus about 80 to 100 kPa, typically around 80 kPa, then you typically reach the limit, and then air bubbles come out of solution, and the sensor does become unsaturated, and so it tends to stay negative. And so if you've got dense soils, you can find that it will go strongly negative. It hits about that almost minus 1 atmosphere. It desaturates the sensor, and it tends to stick there. And if you do a dissipation test, it will come back again. And in soils where that happens a lot, those are the cases where people say, well, why don't we switch over and we'll put the porous element on the face of the cone, so in the U1 location. And in that location, you typically get positive pore pressures because it's responding to the high stresses that you're applying from the cone. And so you tend not to get negative pore pressures there. And so you don't have this desaturation problem. So in these very dense dilative soils, occasionally people will switch over and measure pore pressure in the U1 location. So hopefully that answered that question. Okay, I think I got that question. As I said, when you go through the literature, most of the empirical correlations are based on relatively ideal soils. In other words, soils that are predominantly young and uncemented with little or no microstructure. And in those cases, we know that the empirical correlations work extremely well because there's a long history, both in the laboratory, both with numerical analysis, and of course with numerous case histories to show that they actually give pretty good answers. Some better than others, obviously predicting things like the friction angle in clean sands and the undrained strength in homogeneous clays and OCR in clays work really quite well. Things like modulus, less so, but the empirical correlations have been improved. And of course, if you measure the shear wave velocity, then that greatly improves it because you're directly getting a measure of the stiffness. Usually you have to soften it down to the strain level that you require for design. Now, I spent a little bit of time in this presentation showing that if you measure the shear wave velocity, you have the ability to identify whether or not there's significant microstructure. Now, if there is significant microstructure, we know that some of the correlations will tend to be off because the material you're encountering doesn't match a lot of the historical material to which the empirical correlations were based. And so the reason I proposed that chart was to say, look, if you have a material that has significant microstructure, you need to be aware that some of the empirical correlations may not work as well as they do in the ideal soils. Now, how badly they will be, it depends on how much microstructure there is and what type of microstructure. So, for example, if it's identifying significant microstructure, that's where knowledge of the geology comes in. Because if you know that you're dealing with a very old deposit, so you're anticipating that you're dealing with maybe a deposit that's maybe millions of years old as opposed to less than 10,000 years, then it's got significant aging effects, and that it's going to be stiffer than you would anticipate. You're still going to get a reasonable estimate of the peak strength because the cone is failing the soil, but your estimates of modulus will be off unless you measure shear wave velocity, of course, which is telling you it's much stiffer than you would expect. And of course, if geologically it's a young deposit, but it's indicating microstructure, then it's warning you that there might be some bonding in the material, so it might be lightly cemented. And so therefore, again, the correlations may not be perfect. Usually the estimates of residual strength in cemented clays are good. The sleeve friction is telling you what the remolded strength is, but the peak strength may be off because of the effect of bonding. And so if you read that 2016 paper in the Canadian Journal, hopefully it walks you through why it's important to identify microstructure. And that's why I spent a little bit of time during this presentation so that you know whether or not the semi-empirical correlations can be used with confidence. Of course, if it's a high-risk project, then it's always useful to do additional things. Obviously shear wave velocity with the CPT is good. If you're dealing with clays, then field vane tests are good. If you're dealing with much stiffer material, then pressure meter testing can be useful. Geophysical is useful. So, things like MASW to get shear wave velocity from surface techniques to give you a two-dimensional image of the shear wave velocity, as well as, of course, trying to obtain high-quality undisturbed samples to do detailed lab testing. So for high-risk projects that warrant a larger budget, then taking high-quality samples is always recommended. If it's a low-risk project with relatively small consequences, if you get it slightly wrong, then generally people tend to err on the conservative side and use empirical correlations that tend to be on the conservative side. So hopefully that answered that question. So David, I understood that question. You're saying, am I aware of anybody globally that's trying to, essentially develop a database, and particularly for tailings? And the answer is no. Currently, I'm not aware of anybody that's doing it. What I am aware of is several of the big geotechnical consulting companies, particularly the ones that do a lot of work in the tailings industry, they're all sort of collecting that data through their projects. So the difficulty often, of course, is the data is proprietary, and so they often can't make it public, but certainly they are compiling the data and looking at trends, using these various techniques to see whether or not it's fitting those trends and how it influenced their projects. And of course, on some of these large projects, they often have a lot of that additional data, things like field vane, seismic measurements, as well as lab testing, etc. So they often have all of that additional information to add to it. And so, yeah, there is a lot of data available, but sadly, it's often proprietary in nature, which is sad. But what's interesting is the big earthquake in Christchurch in New Zealand in 2010 and 2011. One of the things that the New Zealand government did, which I thought was an excellent move, is they basically realized that the consultants have said, look, we're going to have to investigate approximately 15,000 sites, and we have to do it quickly, and we would recommend that we do it with the CPT. And so they realized that they were going to get thousands of CPTs all over the city, and they wanted to try and create an open source database. And so they developed a database that said, look, everybody that adds their data to it can have access to the database. So now that database has something like 30,000 CPTs in and around Christchurch. And for the liquefaction world, this has now become a treasure trove of data. And I've encouraged many other regions to follow suit and say, look, government agencies who often have oversight over projects should think about demanding that geotechnical data collected at sites, and mine tailings could be an example, that says, well, every time data is collected at mine sites, that data should be put into a common database that others could access. Obviously, you possibly could remove site details, etc. But putting it into a common database so that everybody could start to share the information. Obviously, that tends to be a little bit harder in the tailings industry because the mines are all owned by different companies and they're often, relatively widely spaced apart, etc. So that may be a little bit more difficult. But certainly in terms of the foundation design, liquefaction, etc., in seismic areas, it's possible that governments can step in. And I've been encouraging, along with others, that the California government, for example, should be trying to duplicate what they did in New Zealand and basically demanding that every time somebody goes and pushes CPTs and boreholes on sites, that all of that should be into a statewide database that others could access to gain a greater understanding of both the geological distribution of material as well as insights into the material behaviors. Oh, ultra soft soils. Yes. Okay. Yeah. So very soft soils. And of course, the CPT got started in Holland because of the very soft sediments in the low-lying land in Holland. So it got started in soft soils. But what we've experienced over the years is as the equipment has become better and more reliable, the equipment is often more robust. So it's designed that you can push into very hard ground. So when you push into ultra soft soils, then what happens is you're often at the limit of the accuracy of the equipment. So, the tip resistance is often designed to go to 1,000 atmospheres of stress, which is 100 megapascals tip stress. So these cones, many of them can go to 100 megapascals tip stress. But if you're pushing into very soft soils, you're actually getting tip stresses below 1 megapascal, well below 1 megapascal. And so you're at the limits of the accuracy. And that's where the manufacturers often sell a range of equipment with different capacities. And so you can get low capacity cones that are designed to push into very soft soils. Now, obviously, you don't want to push them into very hard soils because you could damage them because they only have delicate load cells in them. And so what happens is a lot of larger contractors will often have cones of different capacities. They'll use the high capacity cone first to verify what the ground is. And if they've encountered predominantly very soft soils, they switch over to a low capacity cone, which gives greater accuracy. And when you get into the ultra soft soils, they're often very fine grained, of course, and that's where the pore pressure measurements also become very useful, because when you're pushing in very soft fine-grained soils, the excess pore pressure is often quite close to what the tip resistance is. In other words, the effective stress around the cone is very low. And so the accuracy of the pore pressure measurement often is better than the accuracy of the tip resistance unless you're using a low capacity cone. So the general answer, experience in ultra soft soils is generally very good, as long as you recognize that you have to use lower capacity cones, and usually you have to follow the test procedures very carefully. And the test procedures require you to take zero load readings both before and after the soundings to check that the zero load baseline readings have not shifted slightly. Now, if they shift slightly and you're pushing in dense soils, it doesn't make much difference. If they shift slightly and you're pushing in ultra soft soils, it makes a big difference. And so the need to measure those baselines before and after, and also take care with the unit weight of the soil. You need to get an idea of what the unit weight is, because when you calculate net cone resistance, you're going to take the cone resistances and subtract the overburden pressure. And so you need to have an accurate estimate of the soil unit weight to make sure you've got an accurate measurement of the both total and effective overburden pressure that you will use when you normalize the data. Yeah, well, I'll talk about the flat dilatometer, and hopefully Diego won't get too upset about what I say. Is that the flat plate dilatometer, as you'll hear from the next lecture, is a test that you push in with basically the same equipment, and then you stop and inflate this small membrane to take the readings, and then you deflate it and then push to the next depth. So obviously it's a slower test. because the CPT is pushed essentially continuously. And nowadays there is actual equipment that you don't even have to pause to put a rod on. It's actually a truly continuous test with continuous rod handling. And so the CPT on average is about 3 to 4 times faster than the flat plate dilatometer, which means in many countries, that means it's more cost effective. And here in North America, when the cost of manpower is a significant portion of the cost, and so if you can have a test that's 3 or 4 times faster, then it's obviously 3 or 4 times cheaper. And so often cost dominates. And so the CPT is a faster, cheaper test to do. And it provides data every 1 or 2 centimeters, where the flat plate dilatometer is typically collecting data every 8 centimeters. So you're collecting a lot more data less expensively. But the DMT does provide measurements that are purely in the horizontal direction. So some people do like to combine the two. And so they'll do CPTs and a small number of DMTs. And so let's say you have a project where you're going to do 20 soundings, and you might decide that you're going to do 15 of them with the CPT, and you'll do 5 of them with the DMT. And you'll usually pair the DMT with a CPT, so you've got the comparison. And that software I showed you has the ability where you can load in the DMT data and then have it automatically compared with the CPT data, so you check the cross comparison between the two. The pressure meter, there's 2 broad pressure meters. You've got the self-boring pressure meter, which is a sophisticated, expensive piece of equipment that's generally used in softer soils. And then you've got the Maynard type pre-bored pressure meter, which is generally, well, it is installed in a pre-bored borehole. And the pre-bored or Maynard type pressure meter is more suited for very stiff soils. So in the soils that maybe you're having difficulty pushing the CPT into, then the pre-bored pressure meter comes into its own because you have the ability to do pressure meter. But the pressure meter testing is a lot more expensive. You get a single test at a single depth, and a single test may take an hour to do. And so in one day, you might get 4 or 5 tests done. So obviously, it's a lot more expensive. That gives you less continuous data, of course. And so ideally, people often combine the two, where you might do seismic CPT, push as deep as you can, and then match it with adjacent, either DMT or adjacent pressure meter testing. Pressure meter is usually the most expensive of your alternatives because it's a much slower test. So in terms of speed, the CPT is the fastest, the DMT is a little bit slower, and the pressure meter is a lot slower. And so, of course, the cost is influenced by the speed. Yeah, okay. Well, of course, when you're pushing the cone into regular soils, the soil essentially supports the rods and you don't have a problem buckling. The problem comes is if you push through ultra soft soils, like very, very weak marine sediments, and then you encounter a hard layer. And so, the worst situation is maybe you're pushing over water. So you've got the rods in the water, then you've got the rods in the very soft sediments, and then you hit a hard layer, and there's the risk of buckling. And so the ways around that is, if you're over water, it's common practice that you lower a casing down to the mud line, and then you push the CPT inside the casing so that the casing supplies rod support through the water. That's common practice. And if you're pushing in very soft soils and you're anticipating to encounter very hard soil, like in northern climates, like a glacial till, or in other climates, maybe a rock or a very dense gravel layer. So you're anticipating hitting something much harder. Then typical practice is to watch the data very carefully, because remember, you're collecting data usually every 1 centimeter. And so the cone does sense slightly ahead. And so it will begin to sense that you're approaching something hard. And so in many cases, the operators slow the penetration down if they think they're approaching a very hard layer. There are alternative methods, and some of the Dutch manufacturers, they have an overcasing design where they have a double rod system, where if you're anticipating this problem, you push the cone for a certain depth, and then you push this slightly larger rod that slips over the the cone rods, and you push that down to catch up with the cone, and then they push the cone a bit more, then you push the outer rods. So if you're concerned that that's a problem, there's this double rod system that you can use that provides added support. It's rare that you have to use it, but if you are in these situations of that, you know that you have these very soft sediments over hard soil, then you can switch to this double rod system, which is actually quite effective. Well, no, the cone has load cells at the tip. So the cone is measuring the force right on the tip and right on the sleeve, completely independent of the length of rods above. So it doesn't matter how many rods you got above, you're measuring the force right at the tip. Right, yeah, okay. Well, the first question was the vision cone, so a cone that has a camera in it. They have two cameras in now that have two levels of magnification, one at 1:1 and then usually one with magnification on it. And that was first, well, I can't remember exactly when it was developed, but it was developed well over 10 years or maybe 20 years ago it was first developed. And the people that did research on it, University of Michigan here in North America, did some research, and they I think have ongoing research. And of course what they found is exactly what you had suggested, is that the first thing they found is that, you know, it's rather boring to watch several hours of video of the soil passing the cone, and so quickly people fell asleep watching that stuff, and so they realized that they should try and automate the soil classification, the soil grain size from the vision. And so yes, they have published papers primarily in the ASCE, the American Society of Civil Engineers journal. And those papers, as I said, I think came out mostly from the University of Michigan by Professor Heinrich. I'm not sure I got that pronunciation correct. Yes, they went on and developed sort of algorithms that would interpret those images automatically. Of course, what happens is once you get into fine-grained, it basically says, oh, it's fine-grained, but I can't tell you how fine-grained. It only really works in coarse-grained materials where it can tell you roughly how coarse-grained it is and what the average grain size is, and give you an estimate of the grain size distribution. But it hasn't really caught on in practice, because most people found that it was much easier just to move over and take selective samples. And now with sonic rigs, they're finding out that if you push the CPT with a sonic rig, you just move over and do a sonic hole and get continuous core and pull it up and actually look at it. That's a way easier way to do it than to try and use the vision cone. So as I said, the vision cone is really moving more into the environmental area where people want to see what the contaminant looks like. So if it's globules of oil, they want to see what the oil looks like and how it's attached to the grains, or is it floating in the fluid, etc. Now, as for in-situ testing, you know, I got into in-situ testing 40 odd years ago, and I got into it because I realized that traditional drilling and sampling was inadequate to really tell us enough about the material, and partly because many of the samples were disturbed. And so although we would do lab testing, we're doing lab testing on predominantly disturbed samples. And the drilling, we were only seeing small portions of the profile, not the whole profile. And so I got into in-situ testing, and I very quickly, I studied you know, the CPT, the vane, the SPT, the flat dilatometer, the pressure meter, and the screw plate, etc. And then realized that the CPT was the one that probably had the most growth potential. And over that 40 years, you've really seen a huge increase in the use of in-situ testing. And really it is the future, because trying to drill and take samples and trying to cope with sample disturbance and do lab testing, all of which is very time consuming and expensive, where in-situ testing is actually testing the material in the ground in its in-situ state. And it's clearly advanced significantly in that 40 years, and you're now seeing software that makes it much easier to use. And so equipment is easily available. There's standardized procedures, there's software to help you process the data, etc. So in-situ testing is now easy to do and should be one of your first lines of attack when the ground conditions are suitable, which nowadays is most soil conditions, unless you're dealing with extremely dense gravelly soils or hard rock, etc. And then obviously you've got to switch to other devices such as geophysical techniques, drilling and sampling, etc., and pressure meter.